Welcome, everyone. My name is Cesario. I am currently a postdoctoral researcher at Texas A&M University. I did this work with Dr. Zachary Graisley. He was my advisor. And I want to discuss with you these machine learning-based mixed design tools to minimize carbon footprint and cost of UHPC. So the motivation for this study is related with the fact that the emergence of UHPC in the last couple of decades has coincided with these global sustainability efforts, and rightly so. And the fact that cement production accounts for a very large portion of the anthropogenic CO2 emissions, this has been one of the main factors raising eyebrows whenever we talk UHPC. The first stone is put ask, what about sustainability? What about sustainability? So the fact that we typically have higher cement contents per unit volume, and the fact that we have also higher costs per unit volume with UHPC makes these comparisons in terms of volumetric indexes not really accurate, because we are not accounting for the efficient designs that we get with UHPC, right? More efficient structures and elements that require much less volume. And if we take into account that the really only reporting method for sustainability currently are the environmental product declarations, the EDDs, and the most the typical reported units are in a volumetric base, kilograms of CO2 equivalent per cubic meter. This is not the right metrics if we are trying to compare UHPC, because UHPC will always look bad if we're trying to look in terms of the volumetric environmental impact. So what is the key to show how UHPC is actually a sustainable material? Well, the key is in the mixture design optimization, have the right tools to make the right UHPC with the right performance and right sustainability performance, and also have proper tools that will allow us to evaluate these trade-offs between performance cost and emissions concurrently, because we have to optimize all of these together. So rather than the objectives, I want to use this presentation to answer 4 key questions that I addressed in my dissertation. First one being, can we accurately estimate mechanical performance and mixed proportions with few experimental ones and machine learning or AI in general? Can we also evaluate these changing mixed proportions and mechanical performance in an easy and intuitive way? We have tools that are easily interpreted to do that. Do we have the right metrics to evaluate mixed proportioning and performance on cost and equity efficiency concurrently? And finally, the question that you might have right now is high phase content or high strength, ultra high performance concretes detrimental to cost or to equity efficiency? So the conceptual framework for this study to reduce the experimental runs was basically to use a factorial design based on orthogonal arrays that allowed us to collect very few experimental data and still collect the important points to characterize the behavior inside this domain of ingredients that I'm using. And I will talk about the different ingredients in different stages in the next slides. But basically, we use orthogonal arrays to reduce the experimental runs. And then we use these collected data to model with 2 machine learning algorithms, the KNN and random forest. Then we use an assembled method to get the best out of the 2 algorithms and basically improve our predictive performance. Once we have the predictive compressive strength for this domain, for all the possible mixed combinations, we combine them with embodied CO2, volumetric unit cost, and proper comparison indexes to develop these cost, equity efficiency, and performance density diagrams. And I will talk about the multi-objective test diagrams later on, hopefully in the next dimension. There's a lot to talk about this, and I would not be able to finish a presentation. Now, my design strategy first, to optimize a mix design, to develop my own mix design. I had a two-phase optimization. I started at the binary scale, and I decided to do this strategy because the IPC in the UHPC is very small, very reduced, so it makes sense to optimize the phase, the binary itself first, and then optimize the aggregates content. And my main variables for the orthogonal arrays were the SCMs first for phase A, and the aggregates and fillers and phase B. When we step into the machine learning optimization, we have to consider other variables like loss and ratio n to the one size content, because very small changes will greatly impact the performance. So I used these two machine learning methods and algorithms, and I compared polynomial models to answer, because we always have this question, why AI? We need to know when to apply AI, or when it makes sense to apply it or not. I will not go into too much details on the models, but with these reduced experimental runs, which were basically, I ran 25 mix designs for the first phase for the binary scale, and I ran 15 additional with another orthogonal array, did 25 more for phase B, so in total 65 data points. And as you can see, if we take a look at the correlation plots between predictions and outcomes, the polynomial models will not show a very good correlation, right? So it's a non-linear relationship. Linear models will not give you much out of that, and the errors are also high. Now, with the KNN model and the random forest model, you can see a really good correlation between predictions and actual outcomes. Now, these models are obviously not perfect. You can see I have some outliers over predicting on the KNN and some under predicting with the random forest. But if you can get this type of accuracy in terms of estimating the trends, this with 65 data points, this is already great, because no one wants to run 500, 2,000 experiments in the lab. And we already know the other challenges related to using data from the literature. So there's always a balance here. So can we make this estimation, compressive strength, mixed proportions with few experimental runs? Well, we can if we have the right factorial design strategies. Doesn't have to be orthogonal array, can be anything, and we have the right machine learning models. Because not all the models work with few data points. Now, how can we look at this in an easy and intuitive way? So I developed this concept of performance density diagrams during my dissertation, which is basically a mixed design. So it resembles a matrix of content plots where you have the most important variables in the x and y axis, and the least important variables faceted by columns or by lines. And your outcome will typically be the density of the diagram. So in easier words, if you have a diagram like this and we're trying to optimize the compressive strength based on the binded cement replacement, we could easily pick a mixture in any region of the dark green. For example, 2%, 2.5% microsilica, 45 slag, 10.5 fly ash, and test this mixture in the lab and see if actually these models are working well or not. We can also use these diagrams in the filter mode, so we can exclude mixtures that will not achieve the required design limits. We can use these diagrams to evaluate your machine learning models. It's another problem. Sometimes these black boxes, we don't know what's happening inside, and sometimes the residual mean square error is not enough metric to tell you what's inside your model. We can also use them for categorical predictions. It doesn't have to be just continuous data. So, again, I will not go over the results too much because this is from the previous presentation, but I can tell you that we picked a few measures from the diagrams, we tested in the lab, and 7 out of the 9 measures actually, we got a really good accuracy in predicting the trends at phase A, and at phase B, when we get to optimize the mortar part, basically I was able to identify these measures in pre, which once I validated with the testing through the C and UHPC standard method, I was able to get a UHPC mixture with 155 megapascals compressive strength with more fine aggregate content than binder. And I did this with without using any nano materials per se. I didn't pursue any density packing of the aggregates, no fibers, no special thermal curing, just basically these algorithms and machine learning models with this typical available material. So can you look at these relationships in an easy and intuitive way? Yes, we can do that with these diagrams. So now, if you think about the cost and environmental impacts, most of these efforts have been started by Dr. Miller from University of California, and these metrics are the way to go now in terms of sustainability, because if you take a look at them, they actually account for mechanical performance in and volumetric environmental impact concurrently. So in that work, they developed several indexes. I basically modified one of them to account for the UHPC, because when they did it for the modules of rupture, they didn't use the equation we use in UHPC. And our goal with these diagrams is basically to, with these indexes, is to minimize that. So we want to minimize the embodied CO2 and maximize the mechanical performance. And we can do the same with the cost. Now, just a quick look at these diagrams. If you look at the left, and this is just a pure linear relationship between the contribution of each ingredient to environmental impact, and we compare that to the diagrams, you can see that the trends are not exactly the same. So if you're trying to minimize the embodied CO2, that doesn't mean that you're automatically getting the most efficient solution of your mix design. And the same with the cost. You can see that the relationship is not exactly the same. Just to give a little bit more perspective. So if we compare the mixture with the minimum X column, which in this case would be the most eco-efficient mixture for this index, we can get about 625 kilograms of CO2 per cubic meter, but this mixture would still be more eco-efficient to build this element with this mixture than the mixture with only 552 kilograms of CO2 per cubic meter. So you can see that these relationships are not as direct as we initially thought. You can also filter these diagrams again for mechanical performance requirements. And now the last question. Let's look at if the high content based and high ultra high performance content is detrimental to cost and eco-efficiency. So I gathered some mixtures from the literature, and if you look at the red ones are normal strength concrete, yellow are self-consolidating concrete, green is high strength concrete, and blue is ultra high performance concrete. This mixture over here is the one with the 155 megapascals. As you can see, if our goal is to minimize these indexes, UHPC is not automatically in the worst, as a worst solution as people typically think that it would be up there. As you can see, it's in as one of the top solutions, or at worst case scenario as a middle of the pack solution. So we have a lot of work to do, in my opinion, in UHPC to promote and foster these indexes. develop and derive more indexes for the applications where we use UHPC the most, and we can show with data actually that UHPC is not a material that affects sustainability in a negative way. So this slide, just to give you even more perspective, we can have a mixture with about 1,200 kilograms of CO2 per cubic meter with UHPC, and that mixture have basically the same eco-efficiency as one with only about 450 CO2 kilograms of CO2 per cubic meter, and that's because the reduction in volume that we get with that element for that specific element. So all of these metrics will be important driving sustainability of efficiency going forward. So the answer to these questions is basically my conclusions. So the implications of this study is that it can be used as a guidance to develop emission density diagrams that could be used as proof of optimization for environmental product declarations, rather than just stating what's the kilogram of CO2 per cubic meter of that particular emission. I believe these tools would also facilitate decision making in terms of material availability, accessibility, cost, as you saw with those diagrams. If you don't have one of the materials, you can quickly pick another mix design that would satisfy your mechanical performance. This would also facilitate communication between non-expert personnel that are in the field, but are not expert in either machine learning or materials, but they could easily interpret these diagrams while being major players, per se, in the decision-making process. This can ultimately lift the few misconceptional barriers that we still have in UHPC, promote its application where it's suitable, and encourage innovative mix designs with new materials. So I will not extend too much on future work again, just developing new indexes, more focus on the steel now, and probably also looking into indexes that account for the differences that we can achieve in span with UHPC. So in cases like this, for example, we'll be able to reduce a lot of the supporting elements in design, and also optimize other material properties and compressive strength in general. So you can take a look at these papers. This is my dissertation, will be available in May 22, and these two papers will probably be available in the next 2 months. If you have any questions, if you want to learn more about this, just reach out to me. I can definitely send you my work already if you want to see it. And hope you like the presentation. So